Welcome to my channel. So today in this video we'll introduce a minimum spanning tree. Okay, so we'll see what is minimum spanning tree and what is the goal of minimum spanning tree and how to achieve that goal and what are the algorithms to satisfy the goal to create a minimum spanning tree. Okay, so these four key concepts we'll see in this video, and the next video we'll just go over the algorithms, all these things. Okay, so now, what is a minimum spanning tree? So before starting a minimum, we need to understand a keyword called a spanning tree. Okay, so once we understood the concept of spanning tree, then we'll see that how to minimize and what thing we have to minimize so that it becomes a minimum spanning tree. Okay, so let's start with a concept of spanning tree. Okay, so please consider the given graph. So you can just see a graph here. So total number of vertices here is given for a given graph is 4. Okay, so 1, 2, 3, 4. So A, B, C, D are the vertices. So we have total 4 vertices and edges is a red line which is a link between two vertices. So you have to count the number of edges here. For the given graph we have 1, 2, 3, 4, 5, 6. Okay, so totally 6 edges. Fine. Okay, in this concept we'll just understand the concept of spanning tree. So here we have a understanding definitions. So in the above graph, always your graph will be represented as a pair of parameters, which is nothing but v comma e. V is nothing but a vertices and e is nothing but the edges. But when you are going with a spanning tree, it is also a graph. Okay, in terms we'll represent that as g dash is equal to v dash e dash. So this is your graph of a spanning tree and this is the original graph. Okay, when you are giving g of v comma e is the original graph and g dash v dash e dash, these are the thing which represents the spanning tree for the above graph. Okay, so we just understand how these two or this is different from the original graph. How come this is will be different from the original graph? Okay, so here v dash is nothing but it is a number of vertices in the spanning tree. Okay, e dash is nothing but the edges of the spanning tree. In the given graph, v represents the number of vertices and e represents the number of edges, same like. Okay, but here v dash and v both are same. So we can say that in the minimum spanning tree, number of vertices will be same as the number of vertices in the original graph. So I can say it simply means that v dash is equal to v, which means that the number of vertices in the spanning tree would be same as the number of vertices in the original graph. Okay, but when you just go with e dash, it is not like vertices. Okay, it's nothing but where you have a number of edges would be different from the original graph. Okay, so we can just say that this is original graph and this is my spanning tree which I have created for this original graph. Now this v dash and v are equal, so number of vertices which we created in a spanning tree is equal to the original graph vertices. But regarding the edges means the links. Okay, this will not be equal to the original graph. That is the main difference when you compare with the spanning tree which created from the original graph. Okay, so we can just say that the number of edges, okay, which means that the edges will not be same, but edges of the spanning tree will be a subset of, okay, subset of the graph, subset of the graph. So that's why we represent e dash is a subset of e. Okay, then we can say how to represent e dash. E dash is nothing but the number of vertices minus 1. Okay, from the original graph we just represent the number of vertices from the graph, original graph minus 1. Okay, this is how you represent the edges of the spanning tree. Okay, so two conditions will have to be followed in the spanning tree creation. First thing is number of vertices in the spanning tree would be same as the number of vertices in the original graph. That is v dash is equal to v and e dash is equal to v minus 1. The other important condition is that the spanning tree should not contain any cycle. It should be acyclic graph. Acyclic graph means where we do not go back again to the vertex, the original vertex, which means that, so in the given graph, I can just go to A, from A to D, I can again go from D to C, again I can just go back to A from C. So this is called a loop. I should not do that. Okay, this is called a cycle. This is acyclic. This is not a acyclic graph. This is a cyclic graph. Okay, my spanning tree should be acyclic graph, which means that I should have a graph without forming a cycle or a loop. So when I am starting from a source, I could not return back to the same source again. Okay, only one time I can visit that particular vertex. That is called acyclic graph. Okay, so these are three important conditions you have to follow while creating a spanning tree. Okay, so for the above graph, okay, so for the above graph, actually they have given it is 5 vertices, it is 4 vertices. For the given graph it is 4 vertex now, then we have to give it as the 3 edges. Okay, let me solve it once. Okay, so now for the example of a spanning tree, just consider a graph of 5 vertices. Okay, so if you have considering a 5 vertices, then I can say that V dash is also equal to 5. So we will be having 5 vertices here. So wherever you have green color, these are the vertex. So we have 5 vertices totally, and the edges will be like equal to 5 minus 1, only 4 edges. So 5 is nothing but number of vertices. So number of vertices minus 1 is equal to the edges of the spanning tree. Okay, so we have to have 4 edges here. Okay, so you can see here I do not form a cycle. So this is also a spanning tree. We can have n number of possible spanning trees. Okay, so this is your one possible spanning tree. For this graph, again we can have the other possible also, like this is also a possible spanning tree, and we have like other possible combinations of spanning tree. So when you form a graph without forming a cycle, then it is a spanning tree. That's the thing. Okay, so now how to create a minimum spanning tree? We know that what is spanning tree now. Spanning tree is a tree, okay, it's like a graph actually. So where we have vertices and edges, so vertices of spanning tree will be equal to the vertex of the original graph, and edges will be the number of vertices minus 1. Okay, I should have that many number of edges in the spanning tree graph. Okay, then what is minimum spanning tree? Okay, so we will be having a number of possible spanning tree for a given graph, but here when we have working with the minimum spanning tree, which means that where sum of edges is minimum. Okay, I will be having like in this thing we have like 4 to 5 possible spanning trees, but when you are just going with minimum spanning tree, which means that the number of edges, you just calculate the sum of edges here. So sum of edges is like we have weight associated with the edge, just add up all the weights. Okay, so we have 1 plus 4, 5, 5 plus 5, 10, 10 plus 2, 12. For this spanning tree, the total edge cast is 12. Okay, so again this spanning tree, the edge cost is 5, 5, 10, 10 plus 4, 14. So the first one is 12 and this is 14, and again for this it is 1 plus 3, 4, 4 plus 2, 6, 6 plus 5, it's 11. Okay, so first one is 12, 14, this one is 11. Okay, and this one is like 1 plus 3, 4, 4 plus 4, 8, 8 plus 2, 10. So in among the weights or total edge cost of all the possible spanning tree, we have to find the minimum, okay, which provide you the minimum cost of edges. So here this gives you 12, and this gives you total cost of 14, and this gives you total cost of 11, and this gives you total cost of 10. So among this, which is minimum spanning tree, and this is your minimum spanning tree. Okay, so that's the concept of minimum spanning tree. So minimum spanning tree is also satisfies the properties of spanning tree whose sum of edges is minimum. Okay, so what are the properties or what are the things we have to satisfy? The main thing is like I should not form a cycle. Second thing is like I should add up all the weights and it should be very minimum. Okay, that is the main objective. So this is thing we discussed before. So the edge cost 10 is minimum. So the last one is the minimum spanning tree. This is your MST, minimum spanning tree. When you just speak with a properties of minimum spanning tree, so here if you remove any edge from the spanning tree, then it becomes disconnected. Therefore, we cannot remove any edge from the spanning tree. So my concept is like my edges of spanning tree should be, okay, different from the edges of number of edges from the original graph. So to satisfy that, we should not blindly remove the edge of a graph, okay, which makes you graph is disconnected, which makes the graph disconnected. That should not happen. We should not blindly remove any edge from the spanning tree. So if we add an edge to the spanning tree, then it creates a loop. Therefore, we cannot add also. Okay, we cannot blindly remove and we cannot blindly add any edge to the graph. So in a graph, each edge has a distinct weight. Then there exists only a single and unique spanning tree. If the edge weight is not distinct, then there can be more than one spanning tree. So you have to, like, based upon the weight also, sometimes no, like, oh, the weight will be same. Okay, for example, if the weight of 1 to 2 is 1, again 1 to 5 is also 1. In that case, I can have two different spanning tree. Okay, so here all the weights are unique, so that I can able to go with the following with the weights. If the weights are same, then I can have, okay, different spanning tree, more than one spanning tree, minimum spanning tree. A complete undirected graph can have n minus 2 number of spanning tree. Okay, so every connected and undirected graph can at least have one spanning tree. Minimum one spanning tree is possible. A disconnected graph does not have any spanning tree, because when you have everything is disconnected, I could not create any. Already it is a spanning tree only. Okay, we do not have a spanning tree in that graph. Okay, so in this case we'll just understand how it is possible for the applications oriented. So here when you just see the applications, okay, so now just think that whenever you just connecting a communication network, so where we have n stations, so where you're just going to lay out communication links between two stations, which involves a cost over there. Okay, it involves a cost of resources, the wirings, okay, the budget, okay, manpower, all these things. Okay, so for that we have to come up with an ideal solution which would extract a subgraph term. It is nothing but minimum cost spanning tree. So again we have to construct highways or railroads, all these things now, which connect several cities. Then also we will be using the concept of minimum spanning tree. How we are going to minimize all the resources, okay, with the effective way. Okay, this is the main concept of minimum spanning tree. And suppose if we want to apply a set of houses with electric power, water, telephone lines, sewage lines, everything. Okay, so you have to plan accordingly, and which should, like, cut out all the resources, okay, in the minimum way, in the effective way. So that gives you the main concept understanding of minimum spanning tree. For example, just please consider here for a problem of laying a telephone wire. So we have a telephone central office over here, and we have multiple homes here. So we are going to connect, okay, telephone wire to all the homes. So this will be your naive approach of the applications. Now how we are going to provide a solution for this? Okay, so if you are providing a solution from the central office, I'm just giving each and every house as a unique connection by using a wire from here to here, again one wire, from here to here one wire, and from here to here one wire. So something like this. Okay, so like this. Okay, this is quite expensive, because if you see here, I have a wire connection. Okay, I have a wire connection. So you can see this, the same concept which I told you before. So from the central office, we are just using different and unique wires to connect telephone exchange. The thing is, like, communication link is set between central office to the each and every home. A separate wire is used, which is a complete expensive idea. So where which when you are scaling up the houses, what happens again, you have to bring up more wires, which becomes again costly. So this is the idea or a concept of expensive. Okay, this is not a better approach. when you're just connecting it. This works like when you have a small like houses or small connectivity communication links, then it is fine, like two or three houses it's fine. But when you're scaling up, always your thing will be scaled up when your population increases. Okay, in that regard this will not be working out. So here we have a minimum spanning tree concept now. What happens now? You can see here, we just from the central office we just use only three wirings direct connectivity, and we extend, okay, from this house we are just extending it. So you can see that the wires is like from the central office it has been reduced. So we are just linking the houses, okay, clustering it actually. Okay, so now the length of the wire, okay, connecting the customers has been reduced. This is the concept, a real time concept for minimum spanning tree. So this here is a spanning tree, this is a spanning tree, but this is your minimum spanning tree, which means that where you are going to reduce the total cost, edge cost. So these are the edges, how we are going to reduce the edges, okay, how the thing is like cost cutting of resources, everything is done in terms of a minimum cost of thing, okay, the goal is achieved. Okay, so this is how you have to understand, okay, this is how you need to understand the concept of minimum spanning tree. So first you understood the concept of spanning tree, then we also like incorporated some special features which is nothing but the minimize cost or minimize edge cost on that spanning tree to get this minimum spanning tree. Okay, so if you have any doubts, please ping me in comments. So in the next video, we'll see the algorithms. So actually for minimum spanning tree, we have two algorithms. One is Prim's algorithm, the other is Kruskal algorithm. The next video, I'll just explain how to achieve, okay, how to achieve the minimum spanning tree from the original graph by using a by using a Prim's algorithm. Okay, so thank you, happy learning.